In this video you will learn how to derive the formula for the series connection of resistors based on Kirchhoff's second law, the famous loop rule, and also based on Ohm's law. And you will learn here how to exploit the current equality in an unbranched part of a circuit and how the length and the cross-sectional area of a resistor influences the amount of resistance caused by a series connection. And by the end of this video you will be able to calculate the total resistance in a circuit without any problems and also understand where the formula for this comes from. And finally, as always, there's going to be a summary of the most important facts from this video at the end. My name is Andreas from The Fearless Engineer, and here we go. Now before we start, let's briefly discuss why you should keep watching this video here. You might have made the observation, if you have watched other videos from my channel before this one here, that if you connect various resistors to each other in series without any branches in between, any junction points in between, then the total amount of current provided by a current source, let's say a battery, will drop. Also, depending on the value of the resistor, the voltage drop across each resistor is also going to vary. And the goal of this module is to explain both these effects, this relationship between current and voltage and the value of the overall resistance in a branch, and to derive a formula for various resistors which are connected in series. So we want to compute the overall resistance value of a series connection of resistors. And this is something which is absolutely relevant for many practical applications which you have to do if you are into electronics, which you have to do on a daily basis, so to speak, every time when you design a circuit. Now, the approach is consisting of 4 steps, which we will look at in this video here. First, we are going to conduct a measurement of both current and voltage in order to compute the overall resistance R total. Then secondly, we're going to combine the famous loop theorem, which we talked about in another video, the Kirchhoff's second rule and also Ohm's law. And thirdly, we will exploit the current equality in an unbranched circuit in order to arrive at this derivation of the overall resistance. And fourth and final, we're going to find an explanation approach for this combined resistance value, not from a mathematical point of view, but from a physical viewpoint, using the length parameter of a resistor. Now let's start with the first step, which is about measuring the current and voltage for such a circuit here, a very simple circuit, in order to compute the resistance value of the series connection of individual resistors here. We have a voltage source of 6 volts, we have 3 resistors, 100, 200 and 300 ohms, and what we are going to do now, we are going to measure the voltage drop in this simulation here, 6 volts. We are going to measure the current flow, which is at 10 milliamps, and based on these 2 measurements we can compute the overall resistance of the circuit here, which is 6 volts divided by 10 milliamps, which results to 600 milliohms. And if you look at the values of the individual resistors here, you will find that 300 plus 200 plus 100 equals 600 ohms. So the overall resistance value in such a series connection is the sum of the individual resistances. And we will derive a formula now which does not rely on looking at the overall current flow and overall voltage drop, but without considering the power source, it's possible to arrive at a formula, a very simple formula, to compute the overall resistance in such a circuit. Now, in order to get there, we need to make use of the loop theorem, the loop rule, and also apply Ohm's law. First, let's consider this loop equation here, which we can generate by traversing this unbranched circuit here, in order to also respecting the directions of the reference counting arrows. So the voltage at the source is counted negative because we move against the counting arrow, and all the components across, all the voltages across the resistors are considered with a positive sign because we move into the direction of current flow and into the direction of the reference counting arrows. And the sum of all this here in the closed loop is of course 0, which means we can isolate the total amount of current drop to the left and bring the rest to the right. Then use Ohm's law to replace the voltages with the individual products of resistance and currents, which gives you this equation here at the bottom. So we have all the resistors in there now and also the currents through the various components. And now in the next step, we're going to exploit the current equality, because obviously as the circuit here is unbranched, the current is going to be the same everywhere. It's 10 milliamps in front of the voltage source, it's 10 milliamps behind it, and in between also 10 milliamps, which means all currents are identical. And related to our equation, this means that we can simply replace all the various individual currents by this total current, which enables us to divide by the total current on both sides of the sign here, and this gives us the total resistance of the individual components, which is simply the sum of R1 and R2 and R3. So the formula for resistors in series follows from Kirchhoff's second law, from Ohm's law, and also from the concept of current equality in unbranched circuits, and this is the formula which you should remember. The total amount of resistance is the sum of the individual resistances in a circuit. We can also take a look at this from a physical viewpoint. If you have two resistors which are placed in series, you can also look at these resistors in terms of geometrical shape. Could be a cylinder, could be such a shape as you can see here, a little box. And this box has a length, L1 and L2. It also has a cross-section area, which you can see here on the top end. And if you have seen the video on the derivation of Ohm's law, you might recall this equation here, which you can see on the right side, which basically replaces the resistance, or the inverse of the resistance, with this conglomerate of parameters here. On the left, you have some geometric parameters, cross-section area and length, and on the right, you have some material properties, and these cause a difference between, let's say, copper and aluminum, but we are now looking at simply the geometrical properties. So the cross-section area for the charges passing through the resistors stays the same. It does not change from the perspective of the resistance value of the charges, but the length, of course, for the first and second resistor, the length adds up, which means that with each new resistor, recall that this is the inverse of the resistance value. With each new resistor, the resistance value of the total simply increases in a linear manner. And this means that this equation here shows us that, for example, placing a series of resistors in series increases the length parameter while the cross-section area stays the same. Let's quickly summarize the most important facts here from this video. First, we have seen a simulation which has shown that the total resistance in a series connection is equal to the sum of the individual resistances. That's one of the key points of this entire video. Then secondly, the current through resistors which are connected in series stays the same. That's the second aspect here. Then thirdly, the loop rule, the loop theorem, in combination with Ohm's law and also with the concept of current equality, provides us with a basis for deriving the formula for the overall resistance of resistors which are connected in series. And lastly, the total resistance of resistors connected in series is the sum of the individual resistances. That's all from this video. That's all for now. If you have any questions, please drop me a comment down below. And as always, I wish you a nice day. See you next time here on The Fearless Engineer.